Hello class, welcome to chapter 4. We look at discrete random variables. A quick recap on discrete. We have seen now initially the difference between discrete and continuous. Discrete means countable. You can count them with fingers, which means you jump from whole number to whole number. You don't consider any fractions in between. And continuous would mean something that is infinite, but cannot be counted, rather measured. So we talk about the difference there. And now when we think about random variables that are discrete, then we're talking about random variables like x that take discrete values like 0, 1, 2, 3, and so on, which can be listed. So we're talking about those kind of probability density functions that involve discrete random variables. So to kind of illustrate this, let's start with an example. Okay. So you have you're flipping 3 fair coins. All right. And so you want to know the possible outcomes. So we want to talk about the random variable. So I'll say let x be the random variable. It always takes capital values, capital letters, but x is the most common one, right? So let it be the random variable where we define x to be the number of heads when you get to toss 3 fair coins, okay? The number of heads. When you toss 3 fair coins. So if you think about this, we need to understand our sample space would be all possible outcomes, right? So we're flipping 3 coins. So the possibilities would be that you get head, head, head the first time, right? One of the options. Then you have H, T, H, 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 T. Then you can have T, 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 H, T, 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 H. And you could have T, H, H. And HTT. Let me quickly see if I repeated anything. No. All right. So we have accounted for all the outcomes. Now, when we talk about capital X being the random variable, the random variable is the number of heads when you get 3 fair coins. So look through your sample space. Is there a possibility? Is there an outcome which has no heads? Yes, we have TTT. There are no heads there. So there is a possibility when there are no heads, which means it's 0, right? So the possibility of getting 0 heads. So let me write that there. And then, do we have 1 head? Yes, we have a possibility of getting just 1 head, the THT, 1 head. Do we have 2 heads? Yes, we have 2 heads here, 2, 2. So we have 2 heads. That's another possibility. We're not counting how many outcomes. We're counting if there is an outcome that gives us the possibility of getting 2 heads. So yes, we do have that. Do we have a possibility of getting 3 heads? Yes, we do have that as well. More than 3 is meaningless because you're only flipping 3 fair coins. Can't expect 4 heads in a toss. So you have the random variable listed out like that. And if you look at the numbers, they are listed, they're countable, and therefore these are a discrete set of numbers, right? So this is called the discrete random variable. Okay? So that's an example for us to see how discrete values for x helps you to determine that it's a discrete random variable, and how do probability density functions work for discrete random variables. What do we mean by that again? If you think of the probability distribution we saw, x column and the p of x column, That is what we're trying to do here. And I will give you a general description of how to find the mean and standard deviation of this probability function. And then we'll look at some specific ones like binomial and Poisson. So let me go in to quickly describe discrete probability density function through its formal definition. So a discrete probability density function, the probability density function is known as PDF. So we will say, binomial probability density function, Poisson probability density function. So the shortcut is PDF, okay? Not like the PDF file, but here it means this. A discrete PDF describes the relative likelihood for a discrete random variable to take on a given value. So we're trying to find what P of x equals x would be. It's still not clear for us yet because the definition is pretty strong. So, you really don't understand how it means in regular terms. So the best way to understand this is to go back to our flipping 3 coins example and build a distribution out of it. So to build the distribution, I need the x column and the p of x column. Okay, so let me do that here. So I have x column and the p of x equals x column. Now capital X is the random variable, and the values it takes would be the small x. Okay, and of course p of x is the probability associated with the random variable. So I have 0, 1, 2, and 3. So 0, 1, 2, and 3. I have to build the p of x column. So what is the probability? What is the chance of getting 0 heads? Because that's what x stands for, right? The random variable tells us how many heads you get when you toss 3 fair coins. So I come over here and then I first of all see how many options there are. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possible outcomes, out of which I'm looking for 0 heads. So there is only one out of these 8 outcomes that has a TTT, which is all tails, no heads. So then I come back and write that is the probability, the chance is 1 out of 8 possible options. So that is basically your relative frequency, right? So 1 over 8. Then I go for x equals 1. X equals 1 means we're looking for the options, the outcomes that have 1 head only. Okay. So I come here, 1, 2, 3, no. Okay. So THT has 1 head, TTH has 1 head, and HTT has 1 head. So I see 3 possibilities here, 1, 2, and 3. 3 possibilities out of the 8 that have 1 head. So 3 out of 8 is the chance for tossing 3 fair coins and getting 1 head. What about 2 heads? So come here. So we have HTH, HHT, and THH. Once again, we have 3 options, 1, 2, and 3. 3 options that out of the 8 that give us 2 heads. So 3 out of 8. And 3 would be, x equals 3 is 3 heads. And that's the only possibility, HHH, that gives us 3 heads. So that's 1 out of 8. Now we saw previously that for a probability function distribution, there were 2 conditions it must satisfy. One is that each probability must be greater than or between 0 and 1. So this is between 0 and 1, right? Individually, each one should be between 0 and 1. In fact, I should say equals, because it's okay if 0 and 1 are included, but strictly speaking, we'll only have a strict inequality because the number is between 0 and 8. So therefore, I write it strict inequality. That condition is satisfied. That was condition number 1. Condition number 2 said when you add all of these, all the possible probabilities, they must add up to a 1. Right? That's how you know that you exhausted them all. So 1 plus 3, 4, 4 plus 3, 7, 7 plus 1, 8, 8 over 8. So that also works. Because we built this distribution and we were able to satisfy the 2 conditions, we know that this is a good probability distribution. It's a well-defined one, right? So once we got these 2, now we will maybe try to spin a problem around this. Okay? So if I say, what is the probability that 2 heads appear when 3 fair coins are flipped? Okay, say that's my question. Okay. The way you will write this in statistics would be probability, or P, of x equals 2 heads, right? So when x is equal to 2, what is the probability when x is equal to 2? So all you have to do is go to the table and look at your row that has 2 heads. And the corresponding probability for that is 3 over 8. So you come back and say probability when x equals 2 is 3 over 8. That's it. So when you're looking for exact values, you can see them directly appearing in your table. So if I say, what is the probability that 3 heads appear when 3 fair coins are flipped? You would say probability of x equals 3 equals 1 over 8. All right? So it is pretty straightforward when it comes to something like that. Okay? So you just look at the row where your random variable occurs and you give the information. Next, we talk of law of large numbers. Again, I mentioned this previously in one of the lectures. I want to just define this here. So law of large numbers states that as the number of trials increase, right? As the number of trials increase, what happens is the theoretical probability and the relative frequency, they get closer and closer together. Remember, theoretical probability is what you expect to happen. It's not what really occurs. And relative frequency is what occurs. And so these two things will begin to get closer and closer. What you expect and what actually occurs will coincide as your number of trials increase. Okay. So I'll say the theoretical probability and the relative frequency get closer and closer together. Again, remember that this is not going to work if you're just doing a small number of trials, right? So just like this flipping a coin 3 times, or flipping 3 coins at once, doesn't matter, right? If you did anyways, you can just record the values. But if you're flipping 3 coins and say the first time you flipped, you got all tails, then you keep flipping it like that for 20 times. It's possible that you get all tails each time. It's very unlikely, but it's possible. But if you were to keep doing this for a very large number of times, 10,000 times or 100,000 times, then you realize that this cannot go on like that. There will be at least a point where you'll get a different combination, right? Out of one of those 8 outcomes, you're going to get some combination. So you're not going to always get only all 3 heads. Although that is a possibility, you can see that the probability of that happening is very low, right? Okay, so we talk about expected value. And we have a symbol for this. It looks like a U with a long tail, you know. So it is, I shouldn't say tails, it starts off with a long stroke. So mu, MU is how you pronounce it. Mu is a Greek symbol to indicate expected value, okay. Expected value would be, roughly speaking, a long-term average. And just like the law of large numbers, what it says that over the long term of doing an experiment over and over again, you would expect this value, this average value, showing up. Okay. So what we do is there is again a way to calculate this. So for that, I'm going to show you give you an example so that we can work through that in finding the expected value, or the mu. So this is, again, remember, mean, right? Mean means you add all the numbers and divide by the total number of entries you had. So because you now have 2 columns, which one would you add? So what we do is we will take the x column and the p of x equals x column, right? So we have to multiply these two. So you have x times p of x. that's what we will do here. So the third column will multiply this entry here. This entry and this entry would be multiplied to get the last column. And when you add those up, that's what gives you the mean mu. Okay. So here is our problem. A team plays soccer 0, 1, or 2 days per week. The probabilities that they play each number of days per week are shown in the probability density function table below. For example, the probability that the team plays 0 days per week is 0.2. That's what this means, right? So let's just remember that x here stands for the number of days per week. So 0 is 0 number of days, 1 is 1 day per week, 2 days per week, and p of x would be the associated probabilities. We're asked to find the mean, the expected value or the mean of the number of days each week the team plays soccer. So let's draw the table again. Well, it's thankfully a short one, so we can do it one more time. And remember, we wanted another column. That will be x times p of x equals x. Right? So we already have 0, 1, and 2. This will be 0.2, 0.5, and 0.3. So this column would be 0. I don't want to put another dot because you have decimal numbers. I'll use parentheses to show the multiplication. Okay. So now that gives us, of course, 0 here. This is going to be 0.5. And this is going to be 0.6. Yeah. So, usually what we do is we try to first check if the given table, like right here, right? If the given table is a probability density function by checking each probability to be between 0 and 1, right? You want to do that for each one of them. They're each below 0, between 0 and 1. Then you add them up. 8 plus 2, 10, so it's 1.0. So that also adds up to a 1. So we do all that. We should do all that. Just that they indicated that it's a probability density function. So we just trust that and we go with it. Anyways, so once we've done the third column, our job is to take the sum of them. Remember what we did to indicate the sum? So sum of this column, so sum of p times x equals x column, summation symbol is used to do that, would be 1.1. Okay. What we are told is mu itself, okay, mu, which is the expected value, itself is equal to the sum of x times p of x equals x. So in this case, we got 1.1 as our answer. So what this means is that the team would expect to play on an average 1.1 days per week. So in the long run, if they went on like this, if they did this in the long run, we can say that the team would expect to play on an average 1.1 days per week. Yeah, so I hope that makes sense here for this problem. Let's take a look at this problem. A person plays a bingo game with an expected payout of $10, $25, or $50. The table below shows the probability of winning each amount. What is the expected payout of the game? The expected payout is the context, the language in this context that they're using, right? So this actually means expected value, mu. That's what they're asking us to find. Now, they didn't tell us this is a probability density function. So as I explained in the previous example, if they state it very explicitly in the problem, then you're good to go. But it doesn't really hurt to check them, right? So let's do that. So let's check if each probability is between 0 and 1. Yes, yes, and yes. So first condition satisfied. Now let's see if they add up to 1. So you can see that that's 1. It adds up to 0.61. So if you think of it as 100%, right? 100%. So we only have 61% adding up. So if you subtracted this, what we're left with is 39%, right? So we have 39% that's unaccounted for. Okay. So now because this is a bingo game, if 39% is unaccounted, what it means actually is that this, for this to be a probability density function, you need one more row that says that the expected payout is actually $0, right? For which the corresponding probability would be 0.39. The 0.39 that we just figured was not accounted for. So it is $0. The chance of earning $0 is 0.39. And see how they, left that out. So that is what happens with casinos, gambling, and all that. If we don't understand the chances of earning a 0 is the same as the chance of earning a 10, right? $10. At least in this case, it's a bingo game. So you see that that's missing information there. Anyways, we need this information to make it a sound probability density table. So P of x equals x, and then we have x times P of x. Okay. So 10, 25, 50, and 0, 0.4, 0.2, 0.01, 0.39. All right, so build your last column by multiplying out these two. So 10 times 0.4, 25 times 0.2, 50 times 0.01, and 0 times. And you notice that because it's associated with 0, you haven't really altered the value. You didn't add or take away any information from that, right? So go ahead, use your calculator and compute your values. So I got them to give us 9.5. Again, remember that's your table, but actually what it means is it's $9.50. That's what this means. So what we're saying is this means a person can expect to win $9.50 on average when playing the bingo game. Okay. So we'll just say mu equals expected value. And in this problem, they called it the expected payoff. So I'll say which is the same as expected payoff is $9.50. So you interpret your number there, and then you interpret it in words as well. Okay. A person can expect to win $9.50 on average. Remember, on average. So they must play over and over again in the long term. In the long term, they can earn this amount. Okay, playing the bingo game. Now let's talk about finding the standard deviation. We found the mean, right? Mean is mu, which is your expected value. So standard deviation, again, can be done. This is all done manually. So we're going to use the table to do this. And I want to quickly recall the soccer example, okay? The number of days per week a team plays soccer, right? So I'll just pull that information here for us. We have x, P of x. P of x is the same as x equals x. So just for convenience, I'm going to do this as x times P of x. Of course, for standard deviation, we need one more column, which will be x minus mu squared. Okay? So let me fill this first, and then we'll go into explanation. That was 0.2, 0.5, and 0.3. And we found this product to be 0, 0.5, and 0.6, right? You multiplied the x and the P of x column. Now, when we did add this summation, xp of x gave us 1.1. In other words, your mu was 1.1, right? So you need the mu. You need to compute this first in order to complete your last column. So for the last column, what we're saying is take each x value from here and subtract 1.1 from it and then square it. So let me write that here. 0 from the x column minus 1.1. That difference must be squared. Don't square it and then take the difference. Okay, the order matters. So then 1 minus 1.1 and then square it. 2 minus 1.1 and then square it. The mu is the same value, right, each time? It's the x that changes. So when you square this, you get 1.21, 0.01, 0.81. Of course, feel free to use the calculator. Don't go ahead and just try to do it all on your head. So once you got this column, okay, now we have one more, because we haven't factored in the probability in this calculation yet. So we have one more column which says we have to do x minus mu the whole squared times p of x. Ooh. Okay, so the p of x is 0.2, 0.5, 0.3. You're going to take each one of them and multiply it to the orange values. Okay, so we have 0.2 times 1.21, 0.5 times 0.01, 0.3 times 0.81. I hope you're able to follow that. Okay, and then go ahead and multiply them out. Use your calculator. That comes out to be 0.005. There are 3 decimal places there. 3 decimal places in all of these, right? So watch out for that. 243. Okay. Now, you know how standard deviation and variance are related. Standard deviation, when you square the value of standard deviation, you get the variance. Okay. So if you were to take the sum of this, sum of x minus mu the whole squared times p of x, okay, that will give you the variance. So you need to take the square root of it. So let me just write that. This gives us 0.490. Okay, so I'll come over here to the main frame and I'll say standard deviation when you square it, okay, so I put the square, that is your variance. Okay, if you wanted the standard deviation by itself, then you need to take the square root of the variance. Okay, so what we saw was the green column, that value gave us the variance. Okay, so we need to take the square root of that. Therefore, square root of 0.490, that's a nice, it's a perfect root. So we actually get back 0.7, no decimal places. So the standard deviation for the discrete random variable is 0.7. Okay. So what this is telling us is that we know that there is the data values, right? They deviate from the mean 0.7 points to the left or right. In this case, it's 0.7. What was the definition? 0.7 number of days per week. Okay, so it's 0.7 number of days per week. That will deviate from the mean, which is 1.1. So it will be up or down from this 1.1, which is the mean, by 0.7. Okay, so their spread can be 0.7 in either direction, above 1.1 by 0.7 or below 1.1 by 0.7. We'll do another one. So we'll use the bingo game to, because we found the mean there already, the expected payoff. Let's use the bingo example here. I just say bingo example. And I will just directly get your columns from there. Okay. So x, we need to have a lot of columns. So P of x times P of x minus mu the whole squared, and we need x minus mu the whole squared, that column, times the P of x column. Okay. So the entries here were, I want to put the $0 first. Remember, we figured that out to be 0.39, the leftover. So that's 0.39. 10 was 0.4, 0.4, 25.2, and 50 is 0.01. Okay, and there we calculated this column to be 0, 4, that will be 5, and that will be 0.5. We got this to be our mu, right? Our mu was $9.50. So we're going to use that mu information to square this here. Okay, it's going to be pretty crowded here if I showed you what I'm squaring. But remember, I'm doing the 0 minus 9.5 and squaring it. So that gives me 90.25. 10 minus the 9.5. 10 minus 9.5 is 0.5, and that's what we square. That gives us 0.25. 25 minus 9.5, when you square that, you get 240.25. And 50 minus 9.5, square that, 1640.25. So feel free to pause the video, do the squaring yourselves, and do the table alongside, and you can feel confident about the calculation. All right, and then the last column would be to multiply this 0.39 with the 90.25. So that will give us, so 0.39, this and this, okay, multiply. So I'll just circle that so you can see what I'm doing. So that those two when multiplied gives you 35.1975. Then these two will be 0.1, right? 4 times 25 is 100, so 0.1. 48.05, 16.4025, because you just move the decimal point, because it's basically like times 1, but you have to move 2 decimal points to the left, so that's what you have there. Okay. Here again, you want to sum them. Remember, this is your variance, and the symbol for variance is sigma squared, right? So sigma squared, you want to add them up. So that gives us 99.75. And remember, your standard deviation is sigma, standard deviation, SD sigma, which is square root of sigma squared, right? That's how the root and the square will undo each other. So then you have square root of 99.75, which gives you a long decimal number, but let's round it because it's money. Let's round it to the nearest cent. So 9.99 actually. So sigma is 9.99, and that is your standard deviation when you find this. Okay. So from $9.50, right, your values can vary up or down by roughly $10. That's what this means. Now, discrete probability distribution is a general idea, a general sense of how you build your x's, meaning you choose your random variable and define it numerically, find their corresponding probabilities, and from that we found the mean and the standard deviation. Now, binomial distribution is a special case, and it's got its own parameters, and if it follows, if the experiment has the conditions that are required for a binomial experiment, meaning those are important characteristics that they must follow. If they do, then we can use the properties that we will discuss here related to binomial experiment. It's got its own formula and things like that, okay, to find the mean and the standard deviation, so on. So what are the, right there, a quick intuitive look at binomial. Bi means 2, right? Bicycle, binary. So bi means 2, norm means terms. So binomial, 2 terms, or something, 2 of something. In this case, it means 2 outcomes. So if your experiment can have only 2 possible outcomes, right, in the 3 flipped coin, we had 8 possible outcomes. So that wouldn't be a binomial because you have more than 2. But if you had 2 outcomes, success, failure, yes, no. So just 2 outcomes, then, and provided it follows these characteristics, we're going to list now, then we know that we could use the binomial distribution. So let's start off here. So there are 4 conditions. Sometimes the book will call it as 3 conditions because one of the conditions is kind of redundant. But I want to put them out as 4 separate conditions so you can see them explicitly. So here we have the first condition that says there should be fixed number of trials. So n is the number of trials. Okay, that's the typical letter we use. So n must be fixed, like 20, 25, 100, 7, something. So n must be a fixed number. And then there are only 2 possible outcomes. Just for generality, we call it success and failure. Okay. So only two possible outcomes. We call them success or failure. Now remember, it does not mean that the experiment should be something successful. Okay. So, in my case, in my experiment, I could say all those who are wearing glasses, let's say, eyeglasses, would be my success because my focus is what calls it the success. My focus is on those who are not wearing eyeglasses. And so the failure will be all those who are wearing eyeglasses. On the other hand, if I change my experiment and I say, my interest is in those who are wearing eyeglasses, then my success would be the probability of those wearing eyeglasses, and my failure would be those who are not wearing eyeglasses. So it doesn't have to be fixed on a generally assumed success or generally assumed failure. It just is what the researcher defines to be success or what the problem defines to be success in that problem. Okay. Again, remember, this is for generality. Okay. So if it's something like a medical situation where you're interested in knowing how many surgeries did not accomplish their mission, right? So technically speaking, that would be a failure, isn't it? So in a general sense, that would mean failure. But here, the number of successes that failed would actually be my success because my focus is on how many surgeries failed. I hope that makes sense, right? So do not be fixated on success being something successful. It just depends on the problem description, what we're focused on. All right. Now for the success, we use P, lowercase p, as the probability of success. And for for failure, we call it as Q, which is the probability of failure. So you know that probability of success plus probability of failure must be the entire probability, 1, isn't it? Because we've exhausted everything. There can only be 2 outcomes. So one is a success, one is the failure. If you took their probabilities and added them, you will get 1. So P plus Q will be 1, which implies, Q is 1 minus P or P is 1 minus Q, isn't it? This is like your complement rule, if you recall, because together they add up all the possibilities. And so all the possibilities, the entire probability will be 1, right? And that is what we did in our probability table. We added all the probabilities. It should add up to 1, which means you took care of everything. And in our bingo example, when it didn't add up to 1, we could see the reasoning there was that it was the unaccounted for value actually corresponded to earning $0. And nobody wants to advertise that, right? In a bingo game, they say, oh, you have a 40% chance or 39% chance of not earning anything. They're not going to advertise that. So that's the reason why the table didn't give us that information. So anyways, so that is how we understand P and Q. And then we say, well, these trials must be independent, right? The n trials must be independent. And again, recall what independent means. They must be independent events. That means the probability of one trial should not affect the outcome of another trial, right? So they must not be interfering with one another. They must be independent. They must be separate from each other. One should not influence the other. Okay, so they must be independent and should be repeated using identical conditions. You can't keep changing your factors or players with each trial. They must be identical. So I would say and repeated using identical conditions. Identical conditions. And the fourth condition is the redundant one I was talking about. So what this means is that when we say they're independent, and this is for each individual trial, the probability of success and the probability of failure should remain the same in each individual trial, right? Because one did not affect the other, so the probability will change if one affected the other. Remember, like with the replacement versus without replacement, or conditional probability given that something happened. All those things can change the outcome of the other because they were dependent. But here, because they're independent, in each individual trial, the probability of success P and the probability of failure Q must remain the same. Therefore, we really want to be very, very particular about binomial distribution. You always want to check if these conditions satisfied. So condition number 1, condition number 2, number 3, and number 4. Again, as I mentioned, this is redundant, number 4, but doesn't hurt us to check it explicitly. Let's look at an example. Before going to an example, let me also give some explanation on the variables and all that. So I also wanted to mention that when your n is 1, right, when there's one trial, right, when n is 1 and the experiment has only 2 outcomes and the trials are independent, in this case where n is 1 trial, so it must be independent, it's called a Bernoulli trial. Okay, when a binomial distribution has n equals 1, it implies we're talking about a Bernoulli trial. So it's just a side information for us, just something for us to know. But honestly, this is something you'll see in higher or advanced math and advanced statistics. So it's good to know that something like this is around. Okay. All right. So I just want to give you all the notations here. So binomial probability distribution has discrete random variables, of course. Okay. And if that random variable x, okay, the random variable x has a binomial distribution, this is how we show it, okay? So you see that little squiggly here? That means x follows a binomial distribution, B for binomial, with n trials and P as the probability of success. This is a very crisp mathematical statistical notation to say that x is a random variable with binomial distribution of n trials and P being the probability of success, because that's all you need. You can find Q because 1 minus P will give you Q, right? So we have all that we need in this notation. So I want to kind of help you to understand that. You will read this as x is a random variable, RV, random variable, with binomial distribution with n trials and probability of success P. So you see how long it takes for us to write this down, but the notation is crisp and makes it very, very clear. So remember that we are trying to find all the we're trying to find the distribution here. So we have these following notations. So let's take note of them. So you know that x is the random variable. Which is defined as the number of successes. Makes sense, isn't it? So if I say, number of surgeries in the past 1 month that this doctor has failed in. So so per week, if I say per week, so there's 0 number of surgeries that failed, 1 surgery that failed, 2 surgeries that failed. So you can go on like that, right? So we're able to generate the number of successes there would be how many failed, right? So that's what we have the random variable as. It's always the number of successes that is defined in the problem. Of course, we know P is the probability of success. These notations are so important because especially when you use your calculators, that is how we understand. So we should know what they stand for so that we'll be able to punch in the numbers appropriately. Probability of failure. N is the number of independent trials. If it is a binomial distribution, you will know n because n is a fixed number, should be a fixed number. The mu is the mean. What's really nice is, remember in our discrete probability distribution, we found mean by multiplying the x column and the p of x column and adding it up. Here it is, because it's binomial distribution, the property allows us to use this formula, which is simply n times p. So you're not doing any table as such, right? And sigma, which is the standard deviation, is also really cool. It is square root of n p q, n times p times q. Okay, so we'll do a problem now. So and then we'll try to find the probability, the mean, and the standard deviation, and you'll find it so much fun. It has been stated that about 41% of adult workers have a high school diploma, but do not pursue higher education. If 20 adult workers are randomly selected, what is the mean, variance, and standard deviation of x that follows a binomial distribution of 20, 0.41? Okay, it's all written very crisply for us. So let's start off with what we have. Okay, so we have x follows, or x is a random variable with binomial distribution 20, 0.41. So I want us to understand that this x here is the random variable, discrete random variable. B is the binomial distribution, and that's important because we will be using U for uniform, N for normal, so it's important to know what that stands for. And this 20, the first one, the order also matters, right? So that's going to be N, comma, P. So 20 is your N, makes sense. 20 trials, 20 times you do the experiment. And P is the probability of success, so it must be a value between 0 and 1, so that's 0.41. Perfect. So we've got the meaning of what this x follows, okay? And we also have that 41% here, which is your P basically. But let's define what x is actually representing here. X is the random variable, so it is what is it defined to be? The focus of this problem is that we have adult workers who have a high school diploma but do not pursue higher education. So X is the number of workers, adult workers you can say, who have a high school diploma but do not pursue higher education. Again, remember, this is our focus, therefore this actually stands for the number of successes. This is basically the number of successes. Number of workers who have a high school diploma but do not pursue higher education. All right, now life is pretty simple here because it's a binomial. And so we just have to find the mean, which is mu, mu, right? That's how we pronounce it. And the formula given to us is n times p. Very, very straightforward. So n is 20. That comes from the distribution information, but it's also given to us here as 20 adult workers. So if we were to write this notation for x, we could totally do that by getting that information right from the problem. But they made it easier for us by giving us that information as well. So 20 times 0.41, that gives you 8.2. The mean is 8.2. So what this means is that in a group of 20 adult workers, on an average, there will be approximately 8.2. You can't have fractional persons, so we'll just round it down to 8. There will be an approximate 8 workers who have a high school diploma but do not pursue higher education. So let me just explain that here, okay? And I'll say it one more time. In a group of 20 adult workers, on an average, approximately 8 workers have a high school diploma but did not pursue higher education. Now let's find they asked for both the standard deviation and the variance, okay? So if we find the variance and then we take the square root, that will give us a standard deviation. So let's do that. So the variance would be, let me write variance first, is sigma squared, which is NPQ, and the standard deviation is sigma, which is square root of NPQ. You have to know this connection here. Otherwise, you might feel lost as to what the variance is because you don't have any separate explosive formula. It's just coming from the relation with the standard deviation. Well, we need NP and Q. We have N as 20. We have P as 0.41. We do not have Q given to us, but we know Q is 1 minus P. So do 1 minus 0.41, which is 0.59. Okay? And so if we were to find sigma squared, that's NPQ, which is 20 times 0.41 times 0.59. That comes out to be 4.838. Okay. That is your variance. And standard deviation will be square root of NPQ, which is square root of 4.838. It comes out to be 2.20. Okay. So you can now pull it out and then write out explicitly as variance 4.838 and the standard deviation is 2.20. Remember, these are actually stand for the number of workers. So you cannot round them up, even though it's 4.8, right? You can't round it up to a 5 because you can't account for the 0.2 part of a person that's missing, right? You always round it down. So standard deviation is 2.20, so round it down to 2. So what this means is if you come back here to the mean, again, this mean is rounded to 8, right? So we have 8 as there'll be approximately 8 workers who have a high school diploma but did not pursue higher education. But with the standard deviation of 2, right, this is approximately 2 now. When you interpret, you want to approximate it that way. So you'll say it's, you can have 2 up or 2 below. So you can have 6 to 10 workers. So you're giving a range because you're saying approximately. So 6 to 10, because 2 below 8 and 2 above 8, who have a high school diploma but did not pursue higher education. So you're kind of giving a range of possible number of workers who fall in that requirement. Given the technology today, you might be given some visual problems as well, so be prepared for that. And for those kind of problems, just follow the instructions and play with it a little bit to get the hang of it and how it works. And then you'll be able to answer these questions meaningfully. So let's take a look at this one. I won't be able to demonstrate it by moving things around, but I'll just give you point to you what to do. In a large population, about 10% of adults are left-handed. A researcher takes a random sample of 40 adults and studies their handedness. Use the graph of the binomial distribution to compute the probability that exactly 3 of the adults in the sample are left-handed. Okay? So understand, in a large population, 10% of the adults are left-handed, but you're taking a sample, a random sample of 40 adults, and they want to see if 3 of them are left-handed. What is the chance? What is the probability that exactly 3 of them? And they've given us this binomial distribution graph. Okay. Now remember, the graph looks more like that bell shape that we've been talking about, right? But it is not filled. As you can see, it's got lines. So because it's discrete, you can't jump from this axis here. Okay, this axis here. This is the number of successes. Because that is your x, right? That's your random variable. That's the number of successes. So we have 1 success, 2 success, 3 success. So it is individually. You don't have any success between 1 and 2, or between 2 and 3 as 2.5 successes, or 2 and 2.79 successes. Right? That will be meaningless. So remember, this is coming out of discrete variables, discrete random variables. So that is your x-axis is the number of successes, and y-axis is the probability as they've already given to us, right? This is your p of x. So x and a p of x. So the table that we did for the bingo table or for that soccer example, you can draw that table like this and get a graph out of it. But because this is like more animated stuff, what they've given us is, you see on top, it says the number of trials, and you have the slider bar. So it says n equals 40. So it's fixed at 40. If you slide it accordingly, you'll get a different graph and so on, right? So you want to slide it to 40 because our sample is of 40 adults. And then you want to think about the probability of success. What is our focus here? Then you'll know what the success is. The number of successes is general definition for x. In this problem, our success is getting the left-handed persons, right? So number of left-handed adults. That is our success here. So the probability of success in this case would be the probability of adults who are left-handed. Therefore, you go back to the problem and see, okay, there are 10% of adults who are left-handed. So this implies probability P is 10%, but you don't write it as a percentage. So change it to decimal and you get 0.1. And that's what's indicated here as P equals 0.1. So they've given that information. And we need to find exactly how many adults in the sample are left-handed. So what happens is when you do the slider, when you move the slide, okay, you will be able to see how the graph corresponds. Okay, I'll show it to you in the next graph. Now Desmos is a free online graphing calculator, so we really like using that. And so your homework problems exercises may draw upon graphs that were powered by Desmos, which means you have the ability to zoom in, out, and so on. Okay, so you can play with it. Now what we say is when you adjust your parameters, when I say parameters, what are the parameters? N and P, right? Because in your problem, you know, x approaches or follows a binomial distribution with n, what was n in this case? 40, and p 0.1. So n and p are your parameters. So when you slide these bars appropriately and set n at 40 and p at 0.1, you can then see that if you moved your cursor to the number 3, the third bar, the third one, because that's the probability of success we're asked, right? Let me take you back here. What's the probability that exactly 3 of the adults? So you want to go down to your x-axis and locate 3. And then you can see that green bar there. So that 3 will correspond to a, because it's calculator, it will give you the exact value that it corresponds to, the height it corresponds to, because that will give the probability for it. And you see that that information is given to us down here, which is 0.2003. It's so accurate. Because for us, if we just eyeball it, it looks like 0.2, but it gives 0.2003. So what I would say is, when you set your parameters to n equals 40, p equals 0.1, and look at your x-axis, x equals 3, then we see that it points to probability of x. When x equals 3, the probability, the y-axis, corresponds to the value of 0.2003. Okay. Again, go by the homework problem and see how they want you to write it. Do they want it to be the same way you see it, or do they want it rounded? If it's rounded to 2 decimal places, then it will be 0.2, because 20 is 0.2. So this is 2 decimal places, 3 decimal places. Just depends on the question. Now take this example. A flip of an unfair coin lands on tails 80% of the time. It's an unfair coin, right? So it does that. What is the probability of getting exactly 6 tails in 10 flips? Now, to answer this question, we don't have a visual. So is there a way to compute probability without a visual? Meaning, is there a formula that helps us to do this? So let's warm up to that. Now let's figure out what our because it's a coin, right? You expect there are 2 possibilities, a head and a tail. So right there, you know it's somewhere binomial, but remember you have to go through all the 4 conditions. So condition number 1, there should be fixed number of trials. So we have n equals how many? 10 flips. So we have fixed number of trials. So that's there. Then the probability of success. Let me take you to that, to those conditions. It's be easier for us to recall. So there should be only 2 possibilities, success or failure. In our case, there are 2 possibilities, heads or tails, right? And then P will be the probability of success. So in this case, we have that P really here, the success. What is success here? Success is tails appearing, right? To get exactly six tails. So success is getting the number of tails. Therefore, we have probability of getting a tail is 80%, so 0.8. Okay. Not getting a tail, which is basically getting a head, would be 0.2%. I mean 0.2 or 2%. The end trials must be independent. So each time we flip the coin, it is independent, right? Flipping the coin second time is not impacted because of the way you flipped the coin the first time. They are independent. And they are flipped the same way, so identical conditions are maintained. And because of the individual nature, the probability of success each time we flip remains the same. Okay, so we're checking all the 4 conditions. So I'll just come down to our problem. So I'll just collect what details we have then. Okay, we established that it's a binomial. So we know that x is a binomial with n 10. And what is P? Probability of success. Probability of success. Here it means probability the coin lands on tails. That is given to be 80%, which is 0.8. So if I were to use the notation, then we'll say x is a random variable with the binomial distribution, the parameters 10, 0.8. So we got that. In particular, we're told how many trials there are, right? Yeah. So that will be the number of successes, not how many trials, sorry, the number of successes. X stands for the number of successes. So here we're told that we have the number of tails appearing. Usually we list it as 0, 1, 2, 3, etc. But here they gave us specifically 6 successes, right? Out of the 10 flips, 6 tails. That's what we want. So when you have something specific like this, can I find exactly for 6 tails what the probability would be? We were able to do that visually, right? We were able to kind of slide that bar and fix it for our n and for our p, and then go to our x, and we could find that from the visual. But to do it numerically, algebraically, we have actually a formula that helps us do it. Okay, so what according to the formula, okay, the formula actually presents itself like this. It's a binomial with x, because you need the x, the specific x, n comma p. Okay. The formula is ncx, remember, combination, p power x times 1 minus p power n minus x, which is basically q power x, right? N minus x, q power n minus x. But we like to keep it just between the three variables, x, n, and p. So that's why they do not bring the q. So I'm going to kind of remove this, but I wanted to show you that 1 minus p is q. So the less variables we have, the better it is for us, because we don't have too many things to find. It's enough to have these three things known. And so what this helps us to do is figure out, of course, x, which is the number of successes. N is the number of, let me just write it, number of successes. I know I'm repeating it in so many places, but that should help us to drive home the idea, the definition there. N is the number of trials, and P is the probability of success. So if you translated this for our, oh, by the way, you recall that NCX, it had its expansion. We use the calculator, so it's okay if we don't recall the expansion, but it's important to know that it was NCR when we learned. So if we were to connect this to our given problem, then B of x is 6, 10, and 0.8, right? So if you were to plug this in, that will be 10C6 at MCX. P, which is 0.8, power x, power 6, times 1 minus 0.8, power 10 minus 6. Now you can go ahead and simplify this and do them individually so that you could compute them manually on your calculator. So that's one way to do it. The other way is to use the calculator again, but then use in the graphing calculator, you have the binomial PDF version, and we could use that to get the value here. So in your calculator, you could do 10C6, then 0.8, and 1 minus 0.8 is 0.2. If you plug these all in, you get 0.088080384. I'm giving you the full expanded value. If you were to use the binomial PDF option, then you will have to do second vars, which takes you to the distribution. Together, that will give you the background key, which says DSTR, distribution. Okay, so you'll go all the way down. And actually, you have 1 through 9, and then there's a 0, and then it goes A, B, C. So in my calculator, TI-84 Plus, it is the A option. Okay, so you go to there are two tabs. So stay on the first tab because you have the distribution dist tab and the draw tab. Stay on the dist tab and go all the way down to A, which says binomial PDF. There's another one. It says binomial CDF. We can't use that here because PDF is probability density function. CDF is cumulative density function. So if you are looking for an exact a number of success, like number 6, right? Then you'll use PDF. If you want to use, or say you want to find for at least 6 or less than 6, those kind of cumulative values, then you will use the CDF. Okay, we'll look at some problems that uses the CDF as well. Okay, so for now, go ahead and select that. And then you'll have this view which says binomial PDF. You want to check that, right? It looks like this. And then it says trials. So please enter 10 there. Then it says P, enter 0.8. And it says X value. And that's your X, which is 6. And then it says paste, right? So you just keep hitting enter each time to enter the values and then hit paste. And then it opens up in a new screen. It says binom PDF 10, 0.8, 6. In some calculators, I've seen that it'll take you to this page, to this screen, and ask you to enter the 10, 0.8, 6. So it just depends on your calculator version. Well, hit enter, and that gives you 0.088080384. The exact value we got when we did it manually. So we have, what you notice is even for manual calculation, we kind of relied on the 10C6 option here, the NCR option, to get that value, or you could have done it manually. But again, the option is yours. So choose the one that is definitely easier on you. So here's the next problem. Suppose a dice is rolled 5 times. A success is determined as rolling a 4. What is the probability of getting at most 2 successes? All right, before we actually get into the problem, because this is coming under the binomial section, you probably know that you have to use a binomial. But say this showed up out of nowhere. How do you determine what to do? Because nowhere does it say binomial. And so we want to look for the 4 conditions. For that, the first thing you want to see is, this is rolling a die, so we know there are 6 outcomes, right? But binomial needs only 2 outcomes. But 6 outcomes are all the total possible outcomes. But we need to see what the experiment is and what outcomes it wants from the experiment. So the experiment, or rather the success here, is considered to be rolling a 4. So if you look at that, that kind of changes things for us. Now, rolling a 4 is a success. So the failure is not getting a 4. So any other number other than 4 would be a failure. Therefore, you have only 2 outcomes, getting a 4 or not getting a 4. Okay, so now that we have established that there are 2 outcomes, we now go back and see if there are fixed number of trials. Yes, because we're rolling it 5 times, so fixed number of trials, n is 5. There are 2 outcomes, success and failure. In success is rolling at 4, and failure is not rolling a 4. Then we have your probability of success must remain the same. Well, because it's a die, there's only one face you get out of the 6 faces. So it's 1 out of 6 each time you roll, and these trials are independent because each time a die is rolled, a die is rolled 5 times. So you have independent, and each time you're repeating it the identical way. So we have that. So all these things are working nicely. Okay. So probability of success is, I'll just write here one more time, probability of success. And success here is rolling a die. Probability of rolling a 4. So the probability of rolling a 4 is 1 out of 6 because there's only one face that has a 4 out of the 6 faces. Okay. And X says, what's the probability of getting at most 2 successes? X is the number of successes, right? So usually we're given a fixed number, 2 successes. But here they say at most. So at most 2 successes, this language means less than or equal to 2. You can go up to 2. That means there are more than one X value. So then your X values are that there are 0 successes, right? That's possible, meaning you didn't roll a 4 at all in those 5 times. So 0, 1 success, 2 successes. So you have 3 options here. So basically, we need to find, so our question actually translates to find the probability that we have at most 2 successes, which means X is not equal to X anymore, but is less than or equal to 2. It's not equal to 2, but less than or equal to 2, which is finding probability of X equals 0 plus probability of X, the independent events, right? So remember addition rule, we add them up. There will be no overlap, plus probability of X equals 2, because you're including 2 as well. And we're going to add them up. Now, if you were to do this manually, okay, that will be NCX, P power X, Q power N minus X, right? So NCX 5C0, P power X is 0, right? And Q instead of q, I write 1 minus p, 5 minus 0, plus, for x equals 1, 5c1, p power 1, 1 minus p power 5 minus 1, plus 5c2, p power 2, 1 minus p power 5 minus 2. And you have to compute them each time and then add them up. Okay? So, well, the calculation has been done manually, and that value comes to be approximately 0.961. Just fix that. Now, how do we use the calculator on this one? On a calculator, binomial CDF, okay? That means it automatically does this. Because binomial CDF for this problem would be, it would be automatically calculating this, okay? So you have your values. In fact, if you go to your second distribution, or sorry, second bars to get to your distribution, and of course there under the disk tab, go down to B, because you go past 90A and then B, it says binom CDF. Okay, so hit that. It says the number of trials, enter 5. For P, enter 1 over 6. So trials, P 1 over 6. And X value. It only asks for one value because it's already going to do the cumulative action for you. And then enter paste. And the answer comes out to be 0.964506178. When we do it manually, we tend to round things up. So rounding errors can sometimes contribute to non-matching terms here. But you want to make sure that you can use the calculator to get this answer as well. So to kind of help you with the terminology we use and what function key to use, we see that we use the word exactly in English, which corresponds to binomial PDF in the calculator. And the notation, so for this example, I'm just going to use 2, okay? So this is how you would write this. This is exactly 2 successes, okay? Now, if we say anything that is a range of values, okay, then we use cumulative. So then we will say fewer than. So range of values will be binom CDF. It always adds from the 0 mark all the way to what value you're looking for. So you'll have to do more calculations to get the exact value. So let me kind of give it to you with an example, and I'll illustrate this. So the probability of getting fewer than 2 successes would mean probability of x less than 2, strictly less than 2. So if you use binomial CDF, it's going to give it to you for less than equal to, for which you'll have to subtract it from x equals 2. Okay. So what I will do, what we have to do is then, a little more calculation to get the accurate value. So we'll have to do binom CDF for this particular example, right? So we'll use 5. P was, so the trial is 5, P is 1 over 6, and the X value is 2, okay? That minus binom PDF, because PDF gives you the exact value, okay? So what this does is 5. So it looks like you're entering the same values. But what this does is this is p of x less than or equal to 2 minus p of x equal to 2. Exactly equal to 2. So that this result will give you p of x less than 2. So you're removing when it's exactly equal to 2. So we can have at most 2, which will be probability of x less than or equal to 2. In this case, you could use the binom CDF directly because it gives it to you up to the 2. Okay. So where we have at most, then we can go for at least. If you say at least 2, it means 2 or more. So that'll be x is greater than or equal to 2. And the other one would be more than 2. Which is probability of x strictly greater than 2. For a greater than situation, you will want to use the complement rule. Yeah. So if it is probability of x greater than or equal to 2, it's the same as 1 minus probability of x less than 2. So that everything less than 2 is removed from the total. So 2 and above will be left for you. And probability of x greater than 2 means you want to remove probability of x less than or equal to 2. So 2 and below will be removed. So 2 and above will be remaining. So you'll use the appropriate combination of PDF and CDF and apply the complement rule for these two situations. Okay. Let's talk about Poisson distribution. It's a French word, so you don't say Poisson. It's Poisson distribution. And here, what this does is it helps us to represent the number of occurrences of an event with a name, specific time period or area. For instance, how many accidents occurred in this intersection? So if we want to find things like that, the number of occurrences, we use Poisson distribution. So let me write that out here. Helps us to, it represents number of occurrences of an event that take place within a specific period of time. For that matter, time or area. And here too, we can use the calculator, of course, to help us find the probability density function of a Poisson distribution using the Poisson function key. So here again, I'd like you to quickly recognize where that will be. So we go to second vars, which gives you the distribution, and then go to the distr tab and go right down. We already saw binomial, so you want to go past that. So you see that in C and D, you have Poisson PDF, Poisson CDF. They behave the same way like our binomial. So C is Poisson PDF, and D will be Poisson CDF. All right, so now we're going to look at some problems from binomial and Poisson using our calculator. Let's suppose that the mean number of phone calls you receive per week from an unknown number is 10. For any random week, suppose we want to determine the probability that you receive exactly 5 calls from an unknown number. So if this was our background, then we have to find, for the Poisson distribution, what's the probability that you receive exactly 5 calls out of the 10 you receive on an average. Okay. So what happens is when we talk about Poisson distribution, I haven't described it much in detail because we're using the calculator on this. So as we use the calculator, I'll try to explain to you that those are parameters. Okay. So then we're going to do second vars. Because it says exactly, we have to use the PDF, okay, not the CDF. So this and C Poisson PDF. When you hit that, it shows in previously we saw trials and things like that, right? Here it has the strange symbol. It looks like this. This is another Greek symbol that's called lambda. Okay, so the Greek symbol lambda actually tells you the mean number of phone calls, per week. So in our case, your lambda is 10. So punch in 10 there. Then you know the x value. X value is your the number of times you receive the call. So number of calls received. And in our case, punch in 5 there. So you only have two things here, the lambda and the x value. So 10 and 5, and then hit paste. And that's it. You get your answer. Probability of x exactly equal to 5 here would be 0.0378. You can stop there. It goes on, but I'm just rounding it there. And then go by what the problem wants you to do. And as always, you will use CDF only when you are looking at those range of values, range of x values, not an exact x value, but a range of values. So, another problem. Here's a problem. An animal rescue organization computes that there is an average of 9.4 feral cats per acre of uninhabited land in a certain city. Find the probability that there are fewer than 7 feral cats living on a random acre of uninhabited land in the city. Okay. So the average rate of success, right? Lambda is the average, the mean rate of success. So lambda is the average rate of success. So in our case, it was 9.4 on an average, right? That's the hint was 9.4 feral cats per acre. That's why it's the rate. And then you need the X for Poisson, right? X is 7 feral cats. But we're asked to find what's the probability that there are fewer than 7, so less than 7. So clearly we cannot use Poisson PDF because that will mean exactly, but we need fewer than. And so we have to understand that I have the option of CDF, which is cumulative function, but CDF would give me with the less than or equal to. So what I have to do is I have to find when it is less than or equal to 7 and subtract it from when it's exactly equal to 7. That way I can use the Poisson CDF here minus Poisson PDF. Okay, so remember to follow the same steps in your calculator. And for Poisson CDF, I'll just enter the values that I had here. Poisson CDF, parentheses, I have 9.4, comma, does it say 7? Which is going to give me less than or equal to 7, minus Poisson PDF, 9.4, comma 7. They look alike, but the biggest key is the CDF and the PDF. And so the CDF value comes out to be 0.279170817. Keep it all in the calculator so that you don't have to type them then. You don't recall one of the answers. You can go back and hit enter to recall that answer. And when it was equal to, the PDF gave us 0.1064 key 7902. 8. And the result of these two came out to be 0.172782968. Okay, this is what your calculator will give you. You can always round it, of course, and to the number of decimal places specified. Okay, so when it is strictly less than, we have a combination of CDF, PDF in our calculation. Here comes our last problem. Suppose your favorite celebrity posts an average of 4.1 messages per day on a particular social media website. Find the probability that she posts one message for a random day and round the answer to 3 decimal places. All right, let's check this out. So my lambda will be the average rate of success. In this case, the number of messages posted. Okay. And that's given to be 4.1. Average of 4.1 messages per day. And then your x would be the number of successes, right? In this case, success is the number of messages posted. And here it is just one message per day. So in other words, you're asked to find when it's exactly equal to one message a day, right? So this is kind of easy, where you have to just use Poisson PDF. And then for lambda, you enter 4.1, and for x, you enter 1. Hit enter, and this is what you get. It's on the front. You see the 6. I have a 795, 6795, etc. But remember, we have to round it to 3 decimal places. 068. Okay. Now for your extra practice, you can check these out. So P of x less than 1 will be 0.01657. Try and play with your calculator to see what right operation would give you this. And I'm giving you extra values. I'm not rounding it to 3 decimal places. So go ahead and explore this. Less than or equal to 1, 0.08452. It's greater than 1. And 0.98343. So I hope you'll enjoy these exercises and hopefully be able to figure out all the correct operations for these. So again, just a quick recap. We looked at probability density function for discrete random variables. We learned about the mean and the standard deviation, and then we went into specific distributions such as binomial and Poisson. So we are done with chapter 4, and I will see you in the next video starting chapter 5. See you soon.